Good morning. I'm Dr. E. Kavita, working as Assistant Professor in the Department of Chemical Engineering, SRM Institute of Science and Technology. I welcome you all for the experiment heat transfer through composite lagged pipe. There are three modes of heat transfer: conduction, convection, and radiation. What is conduction? What is the principle involved in conduction? How heat is transferred by conduction? Let us assume a plain wall which is having a particular thickness and thermal conductivity K. Let us assume inside surface temperature as let's say 150 degrees Celsius and outside surface temperature at 30 degrees Celsius. So heat is transferred from high temperature region to lower temperature region, right? So how it is transferred from this high temperature surface to lower temperature surface? So the molecules with higher energy will impart energy with the molecules having lower energy. So due to the movement of molecules, heat will be transferred from inside surface to outside surface, that is from the surface which is at a higher temperature to surface at a lower temperature. So conduction is the actual but invisible movement of molecules through a solid substance due to temperature gradient. There are various applications of heat transfer in process industries. For example, let us assume steam, which is transported from one part of the process to other part. I don't need heat loss from steam pipe to atmosphere, that is ambient. If there is heat transfer from steam pipe to atmosphere, then at the discharge part of the pipeline, I will not get steam. Instead of that, might be water, right? So I need to reduce the heat loss from the pipe to ambient. For that, I can make use of insulation layer. So lagging material can be used or it can be added over the pipe surface to avoid heat loss from pipeline to ambient. But in most of the cases, addition of insulation material on the surface increases the rate of heat transfer. Beyond certain thickness only will get drop over in rate of heat transfer. So the radius at which the rate of heat transfer is maximum, that is called critical radius of insulation, and the thickness can be defined as critical thickness of insulation. For example, for a particular insulation material in the cylindrical form, if its critical radius of insulation is let's say 10 mm. If I am having the insulation material thickness less than 10 mm, may actually increase the rate of heat transfer to ambient. Beyond 10 mm only, there will be drop over in rate of heat loss to ambient. So when I design the insulation layer, the thickness should be more than that of critical thickness of insulation. So the role of insulation material and also critical radius of insulation play a major part in heat transfer applications. So what is the aim of experiment? To determine the thermal conductivity of the lagging material by performing an experiment in an experimental device. So what is that experimental device? So let us see how does it look like and the description about the experimental setup. So experimental setup consists of a rectangular duct. Inside this rectangular duct, we have a hollow cylindrical pipe which is covered with two layers of insulation. So the schematic representation is shown here. So since it's a closed duct, so inside that duct we have the arrangement like this. So it has a hollow cylindrical pipe which is a steel pipe that is covered with the two layers of insulation. Layer 1 is made up of asbestos and layer 2 is made up of sawdust. And we have thermocouple arrangements across this pipeline and the interface between sawdust and asbestos layer and the outer surface of sawdust. The temperature sensed by the thermocouples are displayed through a digital temperature indicator. There is a voltmeter and ammeter to regulate the power supply to heater. From heater, heat is transferred to the cylindrical pipe. So the cylindrical pipe is actually connected with the heater. So by regulating the power input, you can supply required amount of heat to heater, and from heater, heat is transferred to the cylindrical pipe. So what actually happens in the experiment part? From heater, heat is transferred to this hollow cylindrical pipe. From this hot surface, heat is transferred to insulation layer 1, and from insulation layer 1, it is transferred to insulation layer 2 by conduction. Now let us see how to perform the experimental procedure. First, you need to switch on the main, and then you have to set the dimmer start position to adjust the power input to heater. And you need to note down voltmeter and ammeter reading. Allow the necessary time for the system to stabilize. After that, you need to note down temperature data, that is temperature across the pipe, interface between asbestos sawdust and outer surface of sawdust at a time interval of 5 minutes. That is, for every 5 minutes, you need to note down this temperature data till the system reaches steady state. How to identify the system has reached steady state or not? Once the system reaches steady state, the net rate of heat transfer becomes zero. So you will get constant set of temperature data. Once you arrive at constant set of temperature data, you can start performing the experiment. Then the observation data can be substituted in the appropriate equations to find out the thermal conductivity of lagging material. So in this experiment, as I mentioned earlier, in the experimental device, we have a cylindrical pipe which is covered with asbestos layer, and that is covered with sawdust layer. So we are going to find out thermal conductivity of sawdust. It is not like for a new material we are going to invent its thermal conductivity. For sawdust, we have standard values of thermal conductivity. We are going to perform the experiment and find out the thermal conductivity and compare the results with the standard data available in data book. So the side view of the experimental setup is shown in this image. So there is a hollow cylindrical pipe, and its radius is R1, and which is covered with insulation layer 1, and its thermal conductivity is K1, and radius is R2, and it is covered with insulation layer 2, which is sawdust. Its thermal conductivity is K2, and the radius is R3. So T1 is the inside surface temperature, and T3 is the outermost surface temperature. Then let's see how to make the tabulation of observation data. So as I mentioned earlier, the first step, we need to regulate the power input to heater and need to note the voltmeter and ammeter reading. So V refers voltmeter reading, note down that. Then I refers ammeter reading, note down that. The next step of observation, temperature data. So T1 and T2 are pipe surface temperature. T3, T4 are asbestos sawdust interface temperature. T5 and T6 are outer surface temperature. TA is the average between T1 and T2. TB is the average between T3 and T4. TC is the average between T5 and T6. So the temperature data you need to take at 5 minutes time interval until you get constant set of temperature data like this. Once you arrive at this kind of data, you can start performing the experiment. Then we'll move on to calculation. How to make the calculation for finding thermal conductivity of sawdust. We are going to do the calculation by taking the assumption rate of heat input to heater is equal to heat transferred to pipe surface. The rate of heat input to heater can be calculated using the formula V into I, where V refers voltmeter reading and I refers ammeter reading. So this value can be equated with rate of heat transfer to pipe surface, and from there thermal conductivity of sawdust can be calculated. Let's see what is the formula for that. So this equation refers the rate of heat transfer to pipe surface, and that is the composite system. So here we are given with the overall rate of heat transfer equation. So in this equation, K1 refers thermal conductivity of asbestos layer, K2 refers thermal conductivity of sawdust, TA, TB, TC are the average temperature of pipe surface, temperature at the interface between asbestos and sawdust, and outer surface temperature. R1, R2, R3 are radius of pipe, inner pipe, asbestos layer and sawdust. And in the specification, you are given with radius, length of the pipeline, and also here you are given with thermal conductivity of asbestos. By substituting all the known data, the unknown data K2, that is thermal conductivity of sawdust, can be calculated. Next, we'll tabulate the results. Thermal conductivity of sawdust, that can be listed here, and the value can be compared with the standard value available in the data book. Thank you all for listening. Thank you.